Yeah, so yeah, it's my great pleasure to be here. And this is probably the least theoretical talk in today's program. So in this talk, I'm going to introduce a fine-tuning algorithm for large language models. We call it cell play preference optimization. So this is a joint work with my students and also collaborators from CMU. So since the release of ChatGPT, there's a surge of large language models, including both open source models and also closed source models. So the notable, for example, open source models include the Meta's Llama model, as well as, for example, some models, the Gamma model released by Google. So one of the most important tasks for building language models is about fine-tuning the pre-trained language models for specific downstream tasks. And this is something I think people in both academia and also in industry can do it because it doesn't require too many resources. Of course, the pre-training of language model is something more challenging and also demand a lot more resources. And in actually some of today's talk, people talk about optimization. I think that can definitely contribute to the pre-training of the next generation language models. But in this talk, I will be focusing on fine-tuning of language models, which is something I can do even in my lab. So when we talk about the fine-tuning, so usually there are two kinds of fine-tuning procedures. The first one is a supervised fine-tuning. This often takes place right after the pre-training of language models, and it takes a high-quality demonstration data set curated from humans or some advanced language models, such as GPT-4. And we can use the same object function for fine-tuning, the same object function as the pre-training for fine-tuning, but just with a high-quality data set, a relatively small data set. And after supervised fine-tuning, another thing people are doing is called reinforced learning from human feedback, or sometimes we just call it alignment. The data set used for RL from human feedback is different from the data set used for SFT, because in SFT, the data set is in the form of you have a lot of prompts along with the corresponding responses. So it's like a supervised learning problem. You have input and output. And the data for RL from human feedback is different. So it's often in the form of a prompt with several responses. And there's an annotation about the preference among these several responses. For example, A is preferred than B, or A is ranked the highest among a set of different responses. And when we do RL from human feedback, we often fit a reward model first based on the preference data set. And then using this reward model, we can do reinforced learning or sometimes just bandit optimization. So in our previous work, we proposed an algorithm called cell play fine-tuning, or SPIN. So this algorithm can be seen as an advanced version of supervised fine-tuning. So the key idea of this algorithm is, if you think of SFT as a behavior cloning, then this algorithm actually is similar to generative adversarial imitation learning. So the key idea behind this algorithm is we first let the language model to generate a lot of responses to a set of prompts. And then we ask the language model to differentiate the response generated by the model itself and the response generated from the human. And as long as the model cannot differentiate these two kinds of responses, that means the response generated by the model is as good as the response provided by human. based on this idea, we designed an algorithm which is an iterative algorithm. And at each iteration, we just update the model weight such that the model is trying to differentiate the responses generated from the previous version of the model and the human's response. And this is similar to the cell play philosophy or cell play principle used in AlphaSeal. And you can see that on the right-hand side, by doing this iterative fine-tuning, our algorithm is able to improve some model, some SFT model from like 58% to 63% on this Hugging Face Open LLM benchmark. And in today's talk, I'm going to introduce a new algorithm, which is designed for RL from human feedback, the second category. So when we talk about RL from human feedback, so this is the typical process. Actually, I have already briefly mentioned this process. We have some preference data set, and then we assume some underlying model for pairwise comparison. For example, we can assume this pairwise comparison follows this Bradley-Terry model. Then we can use this model assumption to maximum likelihood estimation based on the preference data to get the reward model, which is denoted by R of A. So this R is a reward function, A is some response given the prompt. And once we have this reward function, then we can do whatever our algorithm, for example, policy optimization, proximal policy gradient, and so on. And recently, there's an algorithm called direct preference optimization. The idea of this algorithm is because estimating the reward function will introduce some estimation error. And this estimation error will be propagated into the following reinforced learning process, which is not desirable. So therefore, the idea of direct preference optimization is without estimating this reward model, they direct optimize the policy. So the idea is we can solve the MLE, we can solve the regularized RL fine-tuning problem, and then plug the policy into the MLE problem of this Bradley-Terry model, and then we can come up with optimization problem which only depend on the policy. So that's the basic idea of DPO. However, there exist some challenges when we do RL from human feedback. So the most significant challenge is, human preference is not usually rational or transitive, because you can see that doesn't satisfy the transitivity property. For example, you are given 3 fruits, banana, apple, and orange. So if, for example, you prefer banana then apple, and then apple then orange, if, for example, the preference satisfies the transitivity property, then you can immediately know that this person prefers banana than orange. However, in many situations, it's possible that, for example, someone prefers banana than apple, and then prefer apple than orange, and then prefer orange than banana. So there's a loop. And if you assume the Bradley-Terry model here, this model actually implies the transitivity property of the preference. And therefore, you can see that this model actually is limited in terms of modeling very complicated human preference. Therefore, we propose to, first of all, relax this model assumption to deal with more general human preference. And second, we also use the same idea of cell play to optimize this general preference model to get a better performance. So here's an overview of the SPO algorithm. So it's an iterative algorithm, and at each iteration, the model first generates its own responses for the upcoming iterations. And then the model will refine itself, so update the parameter of itself to output the preferred self-generated responses more often, and then also output the rejected self-generated responses less often. So by using this idea, you can see that on the right-hand side, we are able to improve the win rate of the preferred responses. The win rate of the model compared with the GPT-4 model from, for example, 25% to like 28%, more than 3%. Okay, so this is the overview of the algorithm. There are two players, main player and opponent player. But in this setting, actually, both players are the model being fine-tuned or being aligned. So the main player is just the model, the current model. We want to optimize such that it will win over the opponent player. And the opponent player is the model from previous iteration, which is used to generate responses to approximate the model's policy. And this algorithm will consist of two steps. One step is generate responses for the opponent player or from the opponent player. And the other step is just update the main player to win over the opponent player. Okay. So in the remaining of this talk, I will just show the mathematical derivation of this algorithm along with some experimental results. So if you have any questions, feel free to stop me. So when we talk about language model fine-tuning, usually we are dealing with a sequence modeling problem. So we denote the input sequence by X and the response by Y. So X is often called prompt, and Y is called response. And the language model is nothing but just a conditional distribution of Y given X, parameterized by some parameter theta. And if we are dealing with, for example, autoregressive model, then this conditional probability distribution can be decomposed as the product of p theta of yj. Yj is the j's token in the sequence Y, conditional X, and the previous tokens before yj. And given a prompt X, suppose we have two responses, Y1 and Y2. And suppose one is, for example, preferred than the other by probability P. For example, Y1 is preferred than Y2 given X. So this P Y1 preferred than Y2 given X is nothing but just the preference between these two responses given the same prompt X. And previously, in the Brady-Terry model, we need to make some parametric assumption about this pairwise comparison. But here, we are not going to make any assumptions for this pairwise comparison probability. And we are going to find two policies, pi and pi prime. You can imagine that this pi is the policy for the max player, and the pi prime is the policy for the min player. And these two pairs, they are competing with each other. So for the max player, it will generate Y1 from pi. And for the min player, it will generate Y2 from pi prime. And we want to, and also we take expectation over the marginal distribution over X, and then the expectation of Y1 from pi and Y2 from pi prime. And then we solve this max min problem. So you can see that the max player is trying to maximize this preference probability, and the min player is trying to minimize this preference probability. And this actually gives you a two-player continuous sum game, because you can define the reward for the max player as this probability, and define the reward for the min player as 1 minus this probability. And when you add these two together, actually, it equals to 1. And for this constant sum two-player game, we know there exists a Nash equilibrium, which is a policy pi star. And this pi star actually is the policy for both the max pair and mean pair. And this is the best policy for each of these player in response to the other player's best policy. So then the remaining question is how to solve this problem. So this is a very widely studied problem. And there exists an algorithm by Freund and Shapiro proposed in 1999. They proposed this multiplicative weights algorithm. And this algorithm, you can see that is an iterative algorithm starting from some initial policy, for example, pi 0 of y given x. And every iteration, it will update this policy by multiplying this exponential function to the power of eta times this probability, and then get the new policy pi t plus 1. So one thing I want to mention is you can see that in this exponential function, this probability actually is defined as a comparison between y and the policy pi t. So this actually can be defined as you take an expectation of this probability y1 is preferred than y2 given x when you take expectation of y2 with respect to pi t. Okay. And the intuition of this update is, suppose y is some response that is more preferable, then we will assign higher probability to this response y after this exponential weight update. And we can also write this algorithm in the following like a formula where we introduce the partition function, which is the integral of the numerator with respect to y. However, this update, because of the partition function, is not easy to compute, which makes this algorithm computationally intractable. So the question is how to approximately solve this equation. So we first move pi t of y given x to the left-hand side, and then take log on both sides of this equation. Then we get the first formula in this slide. You can see that the left-hand side is just a log density ratio between the policy pi t plus 1 and pi t. On the right-hand side is eta. This is a step size times the comparison probability minus the log partition function. And we want to, given pi t, we want to find pi t plus 1 such that this equation is satisfied. And in order to come up with an algorithm to find such a solution pi t plus 1, we propose to use least square regression to solve it. We just subtract the right-hand side from the left-hand side and then take square. Because if this, for example, equation holds, then this subtraction will equal to 0. So we want to minimize their difference such that their difference is as small as possible. Okay, and this gives the second equation in this slide. Then the remaining question is this log partition term is not easy to compute. So what should we do? So suppose this optimization problem converges, which means pi t plus 1 will equal to pi t. In this case, the quantity inside the log actually equal to 1, and the log 1 equal to 0. And at the same time, if pi t plus 1, if y is sampled from pi t plus 1, then this pairwise comparison this probability will equal to 1/2. So we propose to just choose this log partition function equal to eta times 1/2, because this is the value of this quantity when this algorithm converges. And based on this choice of log partition function, we end up with the last formula in this slide, which is the object function for this cell play preference optimization. And you can see that in this optimization problem, this exploitation can be replaced by, for example, just a sample from the underlying distribution. And the only term that we need to estimate is that probability. But this probability can be estimated using some pairwise reward models. And the intuition of this training object function is, if, for example, this pairwise comparison probability equal to 1/2, then you can see that log pi divided by pi t minus 0, if we want to minimize this object function, the minimizer to this optimizing problem is just equal to pi t itself, which means we don't need to update the policy. But what if pi actually is preferred than the response generated by pi t on average? In this case, this probability will be greater than 1/2. And this probability minus 1/2 will be a positive number. So by minimizing this object function, we will increase the probability of y given x for the new policy pi t plus 1. Okay. And similarly, if this probability is less than 1/2, you can also do some reasoning to figure out that if you solve this problem, it will decrease the probability of generating y given the response x. So this is the algorithm we come up based on this training object function. So the algorithm is in an iterative way. In each iteration, we first use the previous model to generate a lot of responses, y1 to yk, for each prompt x. And then we are using some pairwise reward model to calculate the comparison probability between any two yk and yk prime. And then we just average this probability over yk prime to get an estimate of the probability comparing yk versus the policy pi t. And then once we have this estimated probability, comparison probability between the response and the policy, we can just solve this optimizing problem in this equation. And then we get theta t plus 1. And this theta t plus 1 is the new model we obtained from the tth iteration. And then we are going to use this new model to generate the new responses for the prompt. So this is repeated for several iterations. And because I mentioned the direct preference optimization algorithm, here I also want to mention another algorithm called identity preference optimization. Actually, it's proposed by McCall and co-authors, and I believe someone also will be either in this workshop or in the code conference. So if you look at the DPO loss function, if we introduce some shorthand notation for example, this log density ratio for YW means the winner response, which is the chosen response for the prompt X. And we define this B as the log policy ratio of the rejected response for the prompt. Okay, so these two can be considered as the estimated reward for winner and the estimated reward for the loser. And then the DPO loss actually is trying to minimize this negative log of the sigmoid function evaluated at A minus B. So you can see that if you minimize this loss function, it actually tries to maximize the difference between A and B. However, it cannot guarantee that A will be increased and B will be decreased. It's likely that A and B both decrease, but B decreases faster than A, so that their difference is maximized. And the DPO loss is also is solving a different object function. So for simplicity, you can think of IPO loss is trying to minimize A minus B minus 1 and the square loss. And in this case, if you minimize the IPO loss, you essentially make A minus B roughly equal to 1. So you still maximize the gap between A and B, but you cannot guarantee that A will be maximized and B will be minimized. And for this SPPO loss, we derived, if you choose, for example, this probability for winner as 1 and the probability for loser as 0, then we get this loss function, which is A minus 1/2 square plus B plus 1/2 square. And by minimizing this object function, we will try to push A to be equal to 1/2, and push B to be equal to -1/2. And this is some thing which is desirable because we want to maximize the reward for a winning response and minimize the reward for the losing response. Okay, so here are some theoretical results. We derived it by following, largely follows the analysis in Fruin and Shapir's 1999 paper. So I'm not going to go into the details of the proof. And in the remaining of this, maybe 5 minutes, let me show some very interesting. Oh, okay. Yeah. So if you are solving this multiplicative weight update algorithm, if you run this algorithm, then after capital T iterations, you first calculate this mixture policy, which is the average of pi 1 to pi t, and then you evaluate these two pairwise comparison probability. One is pi greater than the pi bar t. You try to maximize pi, and the other one is you try to minimize this one. And their subarithmetic gap will be in the order of 1 divided by square root of t. Okay, yeah, okay. So in the rest of time, I will show some experimental results. Okay, so the first result I want to emphasize is you can see that during the fine-tuning process, for the DPO loss, the estimated reward for the winner and the estimated reward for the loser, both are in the orange color. Actually, the winner's reward does not increase, but the loser's reward actually decreases a lot. And in this way, it maximizes the gap. But it's not does not meet our expectation because we hope during the fine-tuning, the reward for winner will increase and the reward for the loser will decrease. And for our SPPO algorithm, you can see that during the fine-tuning, the estimated reward for winner will increase and the estimated reward for the loser will decrease. So this is consistent with our algorithm design. And let me show some experimental results here, maybe on the right-hand side. So you can see that after 3 iterations of SPPO, we are able to improve the base model, which is a Llama 3 8 billion model, from the original win rate of 22.9% to 38.8%. So more than 15% increase in the win rate, which is considered as a very significant improvement. So in the intro time, I will just summarize what we have done in this work. So we propose a self-play algorithm for preference optimization to align the language model with humans' preference. And the derivation of this algorithm is based on the, trying to find the Nash equilibrium to a two-player constant sum game. And we also use some experiment to validate the effectiveness of our algorithm. And it shows that this algorithm indeed outperforms the very strong baselines such as the DPO and some other strong baselines. Okay, with that, I will stop here. Thank you. Oh, yeah. So because in our algorithm, we need a pairwise reward model. And in our experiments, we just use a very small reward model of size 0.4 billion. So it's a very, very small model. We do not use any supervision signal from GPT-4 or similar advanced language models. We're starting from this base model. We are using a very small reward model. Then we are able to improve the win rate of, for example, Llama 3 8 billion from 22% to 38%. And actually, it even outperforms the older version of GPT-4, which is released in March 14. Yeah. So that's the last bullet trying to emphasize. Yeah. Mm-hmm. Yeah. Yes. Yeah. Yeah. Yeah, yeah, it's possible to get a faster rate. Actually, we have another work. We can improve the rate, but by using some extrapolation, like Nassau's momentum. Yeah, by using that, actually, we can improve the convergence rate of this algorithm. Yeah, it also performs better in practice. Yeah. Yeah, thank you. Yeah. Any other questions? Oh, question. Oh, that's a good question. So this is like a heuristic choice of the log partitioning function. But the motivation behind this choice I already explained, because when this algorithm converges, which means when pi t plus 1 equal to pi t, then the first term, this log density ratio will equal to 0, and this pairwise comparison will equal to 1/2, because you are basically comparing pi t with itself. And we want this loss function to be equal to 0. So that's why we choose this log partitioning function to be eta divided by 2. No, so I think this is this part, the choice of the log partitioning function is indeed from our like ad hoc choice. So there's, as far as I know, there's no theoretical justification for that. Oh, okay. Oh, overfitting to this reward function. No, because this reward function is actually a very weak reward function. There's a reward benchmark, and this reward function is not ranked very high. Actually, it's ranked, I think, is outside of the top 10 reward function. The reason we choose this reward function is because in our algorithm, we need to annotate the pairwise comparison. So we need a pairwise reward model rather than pointwise reward model. And there are not many pairwise reward model out there. So, but this reward model is one of the very few pairwise reward model that is publicly available. So that's the reason we use this reward function. Yeah. All right. Yeah. Thank you.